you see my
Okay,
screen?
yeah. If you can put full screen.
Hello? Luca,
Yeah.
can you see my screen?
Yes, I can see, but it's not full screen yet. If you can make it full screen.
Okay, I can do it. What about now?
Yeah, now it's perfect. So, okay,
Okay.
please, you can start.
Okay, thank you for inviting me to this nice conference. Actually, didn't attend all the talks. I apologize for this. And moreover, let me thank Luke in particular. So in this presentation, I would like to review and also provide some news about non-local quantum gravity. So this is a proposal of a gravitational theory, which is unitary at perturbative level and super normalizable. Moreover, we can also show that very simple extension of the action I will review in a few minutes can be made even finite. This is easy to be done in odd dimension, but not that complicated even in even dimension. Other topic I would like to touch is about causality, and this is strictly related to amplitudes. In the last, it depends on time, of course, I will mention conformal symmetry and in particular a new theory which includes also matter. So let me shortly list here a few theories before to touch the non-local actions and in particular to introduce non-locality. So everybody knows about Einstein-Hilbert theory, the Starowiecki theory, the Stelle theory. I here would like just to point out, because these actions had been reviewed and even the past days, that about the Stelle theory, there are good news in our days, and though this is true also for the Azurey Lopez Shapiro, these theories are actually unitary. So we can easily make these theories unitary using, well, me and Shapiro, we prove the unitarity level. That's not a big deal, but more recently, Anselmi and Piva were able to prove the unitarity of these higher derivative theories, local higher derivative theories. They will be able to prove the perturbative unitary at any perturbative order. Okay, this is everything I would like to say about higher derivative theories, and then let me move to non-local gravity. So the action that I will mainly focus on is this kind of action proposed in the past by other people before me. And so you see, it consists of the usual Einstein-Hilbert term, and there is this funny form factor, which is an analytic function in between the Einstein tensor and the Ricci tensor. What is the exponent? The exponent h, first of all, is an entire function of the D'Alembertian operator, and this is the ambiguity and the weakness of the approach, but we will see later that we can also make at least one unique prediction coming from this theory. So the main form factor I will focus on is an asymptotically polynomial form factor, because using this particular form factor, we can apply the usual power counting analysis. And the main property is that the asymptotic limit of this function here turns out to be polynomial plus corrections that do not affect the divergences. So they do not affect the beta functions, which are for me the coefficients of the the contribution which appear in the divergent part of the quantum effective action. This is very powerful because then we can have under control the divergences like in higher derivative theories. We can generalize, and indeed we can introduce this. It's not the most general one, but this is a quite general action which contains 2 up to 3 form factors, although the gamma 4 form factor does not contribute to the propagator in Minkowski spacetime. And in order to achieve perturbative unitarity that I will touch in a moment, you need to select these 2 form factor gamma 0 and gamma 2 in a special form, depending on the entire functions h0 and h2. You can also add this operator, which is a local, could be also non-local vertex operator. By vertex, I mean operators that depends at least on 3 curvature, but cannot exceed the number of derivatives which appear in the form factors in the UV limit. The exponent h0 and h2 can be choose like in the previous slide, having this polynomial asymptotic behavior. Gamma, if we will meet again in the next slides, is an integer like the previous n appearing in the polynomial. Okay, so in the past, also other particular choices of these four factors had been studied. Somebody like, for example, this theory in the Weyl basis, because it is suitable in order to address the some issues in cosmology, like in order to accommodate the Starobinsky model in a UV complete theory of gravity. And you can see there is an extra pole in this four factor, which is the maximum spectrum we can have for this theory. So at most we can have the graviton and a scalar degree of freedom, at least the graviton scalar degree of freedom. Of course, then from the observative point of view, it's not easy to discriminate in the Jordan or Einstein frame where this scalar is. But this is in principle a falsifiable theory if you find more gravitational degrees of freedom. So now to claim the theory to be a good perturbative theory at quantum level, we should prove at least two things: unitarity and renormalizability. And we will see actually this theory not only renormalizable, but is actually super renormalized. Let's touch first unitarity. What unitarity is? First of all, you have to compute the graviton propagator. You expand in graviton perturbation around Minkowski. You are at this moment considering the perturbative unitarity around Minkowski, also because the unitarity is only defined around Minkowski space-time. Otherwise, you can talk about stability, but that's another story that I don't want to consider at the moment. So if you take the four factors I introduced previously equal, and then the theory is exactly this one, the propagator turns out to be exactly like the Einstein-Hilbert propagator times a function that has no pole at finite distance in the complex plane. This is not enough. If you want to be more quantitative and prove unitarity at 3 level, you have to take the S matrix. Unitarity is S dagger S equal 1. And if you agree on this, then you take your propagator, which here is defined with all the I in the right place. I'm using here actually signature, which is minus plus plus plus. And unitarity, or in other words, S dagger S equal 1, is equivalent at 3 level to evaluate 2 times the imaginary part of the amplitude n. What is the amplitude? Well, the amplitude is the amplitude you compute taking the sandwich of the propagator in between two energy momentum tensor, the most general energy momentum tensor. At least this energy momentum tensor has to be analytic, because of course, if you introduce other poles in the energy momentum tensor, like in theories that have non-locality in the infrared, then this analysis does not apply. But in our case, it works because the theory has no non-locality in the infrared. So you take, you can compute the imaginary part. Here is, you can see explicitly the computation. I mean, shut up and calculate. So you take the propagator, you use the tensor structure of the propagator, and you have these contributions in any dimension. And in particular, you can, with the Feynman prescription, you have, I don't know where to move this, okay. With the Feynman prescription, you end up with this kind of contribution. You take the imaginary part, and it turns out to be exactly the same of the Einstein-Hilbert theory, just because we consider 4 factors H2, H0 in general that are 0 in k squared equals 0. So you see, this is perfectly positive. Okay, that's just a 3-level unitarity. Now, what we have to do is, in general, to also address the issue of unitarity at perturbative level. So when you compute loop amplitudes, and this can be done. For example, for a scalar theory. Since I want to present here explicit computations, even because the organizer asked me to present computations, I mean, to some details about unitarity and causality, let me consider this bubble diagram. The idea in this theory, also touched by other authors before me and after me, and in particular thanks to efforts of Brichese and my students, so you can compute the bubble diagram. The main point is that the amplitude has to be defined as an analytic continuation from the Euclidean space to the Minkowski space. It means that in the beginning, all the momenta, even the external momenta, are imaginary, are complex, and afterwards you make you move P0 from having only imaginary part to become real. On the other hand, the momenta on which you are integrating are always complex. When you do this operation, and here I have in mind the two propagators over here, there are 4 poles at one loop, since there are 2 propagators. 2 poles, actually, k bar 1, k bar 2, do not move. You will see in a moment why from the explicit formula. While the other 2 depends on p, and when p0 goes from complex values, purely complex value to real value, then these poles, the pole for K4 pinches the imaginary axis, and it ends up somewhere in this region. So the point is that now the analytic continuation consists in integrating on this funny path. So let's do it. So how to compute it? Here is the explicit computation. You have mi, which is the integral along the imaginary axis, and the residual, because of the Cauchy theorem. And mi is this integral now, where I replace c, the funny path, with I, and the other one is the residue evaluated in K4. You can show that these 2 contributions, actually the second one only gives contribution to the imaginary part, or in other words, to the discontinuity. And the result is exactly the same of the local theory, where there is no 4 factor here. Actually, there is b, but you can always take 4 factors for which b is 1 when you evaluate the residue. And you will see this in a moment. Okay, this is something you can do. You can do at any loop order, but let me do the explicit computation, actually, to a certain point at least. So mi, first of all, since you are integrating along the imaginary axis, you can change k0 in ik4, and your integral from imaginary became in r times r3. And the other important thing is here that, well, nothing else. Here are the 2 propagators with the pole that I already told you what properties are, where are in the complex plane. So let's take p equals 0 just for simplicity, and in M there is this. This is the expansion of the exponential that you see here, because K4 is real, but P0, sorry, yeah, K4 and P0 are both real now, and then there is this extra exponential I, and when you make everything explicitly, you see there are 2 contributions. One is real, one is complex. But if you look at the complex, the complex part of mi, you see that since this function is odd in K4, when you integrate in K4, you get 0. So from mi, you don't get any contribution to the imaginary part of the amplitude. Then the imaginary part would come eventually from the residue. And in this is what you get. There is, even from that part, a real contribution, but the imaginary part is exactly the same of any local theory. Notice that here I selected this 4 factor, in which on shell you get exactly e to the 0, which is 1. So this proves, not only for this particular 4 factor, but for any 4 factor, that the imaginary part of the amplitude with this analytic continuation is the same of a local theory. What about then this extra contribution? This is the leading one. I mean, this is the extra contribution, but it's real, has nothing to do with discontinuity. So unitarity is gone, it's done. Now I want to tell you a little bit more about the real part of the amplitude. So the real part consists on this contribution, which comes from the residue too, And it is very divergent for e to the box. For this particular form factor, it's very divergent in the UV. Here are the plots. You can see the real part in the infrared is very similar and very close to the local case. But when you go in the UV, you get this behavior. And so it goes to minus infinity in this case. On the other hand, the imaginary part has the usual form. So you see this form factor, actually this gives this kind of contribution to the amplitude. We can make some mentions, but I don't want to make these comments right now. Just let's study the unitarity and some properties of the real part. We can do better if we take the exponential of box square. In that case, I don't know. I have, oh, okay, there are many stuff here. If you take e to the box square, then you can improve the behavior. And indeed, in the infrared, so at low energy, you have the same, a real part, which is almost the same of the local theory. But when you go at high energy, I mean infrared, I mean respect to the scale lambda, the non-locality scale. But when you go in the ultraviolet regime, it goes to zero very, very fast. And it goes to zero with the error function that a lot of people like a lot. At least this is the computation, the analytic computation for m equals 0. Otherwise, you don't get this nice function. So you see the difference, and explicit computations to prove with calculations unitarity on one side and some properties of the bubble amplitude for these two particular form factors, but the feature will be very similar for other form factors, depending on the even power here or odd power. Okay, now Fabio also studied amplitudes with any number of loop, and he also took care about anomalous threshold. You can prove exactly the same Katkowski rules of local theories, and the discontinuity is the same of the local theories, and there are no doubts about unitarity in this analytic continuation approach. So unitarity seems okay, is okay. What about renormalizability? The other property that we would like to have. In order to make short and in a nutshell the renormalizability property of the theory, we can focus on the theory in the ultraviolet. This is actually the polynomial behavior in the ultraviolet for a general theory in d dimensions. And the propagator in the ultraviolet, there are no extra poles here. This is the behavior in the ultraviolet due to that particular form factor. It has nothing to do with extra poles here, just to give an idea of the scaling. The propagator has this kind of behavior. For example, in d equal 4, it could be 1 over p to the 10th power. And since you have general covariance in this theory, then also the vertices have exactly the same leading behavior. The implication is that in the end, when you make the usual, here is a rough power counting estimation, you get that you are able to remove all the divergences if gamma, the integer gamma here, is big enough. So if you take gamma bigger than 3, for example, in d equal 4, then you have divergences only at one loop. You are able, with this, in this particular unitary theories, to remove all the divergences beside the one loop divergences. At least with this particular model, with this particular, looking at this behavior in the UV. But we can add other operators, and I will show you later how to make the theory actually final. So you can check that the result is consistent with, at least formal, with Einstein gravity, with stellar gravity. And the counter terms, let's focus on 4D, are the usual at most, how many are these? 6, because there are also boundary terms, topological terms, and so on. So you can shortly say that up to particular requirements on the boundary conditions, you have these two the operators that so you have these two operators in the quantum effective action. These two divergent contributions to the quantum effective actions. But at most, you have divergences only at one loop. You have to renormalize only a finite number of couplings. which are at most 4 or 6 in 4 dimensions. Okay, so a little bit more technical details. First of all, how many minutes do you have?
You have 8 minutes.
Only 8. So let's make the story simple here. I just wanna, maybe you can read later if the slides will be uploaded somewhere. So the point is that in this particular theory, even if it seems so complicated, you can figure out what is the behavior of the running couplings, which are, as I said, at most 4 in this quadratic theory, because on the beta functions do not depend on the running couplings. So you can integrate, it is straightforward, the integration, and you get this running of the coupling constants, all of them, which are at most, I said, 4 or 6. Let's focus on one particular coupling, which is the Newton constant. It's running this one. Beta is a constant, depends only on the theory in the UV, but the operators are Eiger derivative and do not renormalize. So the beta functions do not depend on the coupling constants. That's the point. So you take this particular scaling and you can prove asymptotic freedom. Asymptotic freedom means physically that the theory is free. The graviton is free in the ultraviolet. And indeed, like in QCD, you can rescale your Lagrangian with K, if K is the only coupling to scale, and you can design a theory which does that. So when you make the rescaling, you have the kinetic operator and vertices. So asymptotic freedom means that these vertices are suppressed with respect to the kinetic operator. This is true for any of these Eiger derivative operators. So in the end, you can reconstruct this structure, and the theory is asymptotically free. This has also impact on something like the trans-Planckian problem in cosmology, or the causality violation as addressed with Fabio. So can we do better? Can we go beyond the renormalizability? Well, that's very easy in extra dimensions, and can be done, however, also in even dimension. Let's focus first on odd dimension, because it's very simple. In odd dimension, dimensional regularization, you don't have one loop divergences. Since this theory has only divergences at one loop, so the theory is finite in odd dimension. For example, in 5D, this is the theory. In 11D, if you like, for some reason, this is the finite theory. What about even dimension? Because as far as we know at the moment, we live in 4 dimensions. Well, with LESDAF, we were able to figure out that an easy extension of the theory, which contains 2 quartic operators in the Ricci tensor and the Ricci scalar, are enough to make the theory finite. Indeed, these operators give a contribution to the beta functions, which is linear in their front couplings S1 and S2, that do not renormalize because these operators are Eiger derivative. Therefore, you can always find a solution of this system for S1 and S2. Okay, we don't have yet all the beta functions, but doesn't matter. If C1 and C2 are 0, it means that S1 or S2 or both are 0, and we don't need the killers, which we call these operators killers. Otherwise, we can always make the theory finite. This is one loop exact, because there are no divergences at 2 loops. So you fix, and you have defined your theory once for all. Okay, here are the computations that already I think Elia showed, and let's now speculate about a little bit about conformal symmetry. So in the ultraviolet, you can have an asymptotically free theory, or like I showed, a finite theory, and therefore a theory which preserves conformal symmetry or Weyl conformal symmetry. And you can make this theory indeed very easily conformal invariant in the conformal invariant. The symmetry is preserved at quantum level, so is anomaly-free, and you can believe in this symmetry also for other purposes, like, for example, solving the singularity issues and other things. Scattering amplitudes. Well, with my collaborators 2 years ago, we computed the scattering amplitudes for this theory without the Riemann square. With the Riemann square, everything changes. And what we found is that the scattering amplitude of the theories that I just presented, in particular, you can rewrite in this form, is the same of Einstein-Hilbert theory, okay, at 3 level, And therefore, we can well, we investigated the reason, and the reason is related to a field redefinition that does not change, of course, the spectrum of the theory. So a field redefinition is good when it does not change the field redefinition, and it is analytic. So anyway, beside the reason, we have the three-level amplitude for the theory. So we can address somehow, partially at least, the causality issue. The causality issue, well, we can, for example, take our three-level amplitudes and use results by other authors where they only use three-level amplitudes to prove modifications to the causality of the theory. Here we don't have modifications because they are the three-level scattering amplitudes are the same of Einstein theory. Then we can do a little bit more. We can resum, at least in the range limit, in the iconal approximation, ladder and cross-ladder diagram. And again, the quantity, the main quantity depends on the three amplitude. So if depends on the three amplitude, if you take a theory like Gauss-Bonnet gravity, you can prove that you have, I'm talking here about the Shapiro time delay, you can prove that delta t is could be actually negative, but in our theory it doesn't happen because the Shapiro time delay is the same of Einstein-Hilbert theory. Moreover, we did the computation also coupling the ordinary two-derivative theory to non-local gravity, and even in that case there is a modification, but still delta t is positive. So there are no causality violations. Here by causality we mean macro causality. Now, finally, I would like to briefly mention the theory including matter. Because in general, matter can spoil many of these properties. And the best way in order to get a UV finite or superior normalizable at the same time to have good properties at quantum level is to take this kind of theory that I'm going now to explain a little what these operators are. So L...
You have 2 minutes, Leonardo.
Yes, I will finish with a couple of slides. L is actually, well, double L here, is actually the local Lagrangian that you wanna make ultraviolet complete or whatever property we are looking for. And you can think about Einstein-Hilbert plus matter, but this technique applies to any theory, even in 0+1 dimension or whatever. And then you take a quadratic operator in the equations of motion of the local theory. In between, there is a form factor, but it's not so ambiguous for factor, even though still is not unique, but is a function of a particular operator, which is exactly the Hessian operator of the local theory. So everything here is completely defined. Why this particular choice? Well, because if you compute the equations of motion, the equations of motion are an exponential times the local equation of motion plus corrections which are at least quadratic in the equations of motion. This implies, and here is actually proved, this implies that first you have all the same solution, okay, you have all the same solution of Einstein's gravity. Second, you have the same three-level scattering amplitudes of Einstein's theory with the implications that I mentioned about causality. Moreover, thanks to other results, we before to introduce this general theory, the stability analysis is the same of Einstein's theory. In other words, Minkowski and all the other spaces that are stable in Einstein's theory are stable in this theory at linear and nonlinear level, depending on what is the property of these solutions in Einstein's theory. So the stability analysis for the Einstein solution, I mean, solutions of E equals 0, are the same of the Einstein theory, and moreover, they have the same stability property. For example, the Christodoulou-Kleinerman stability analysis of Minkowski space-time is the same in this theory, at any perturbative order, linear and nonlinear. Finally, the theory is super normalizable or finite and unitary. Well, last slide is something I'm quite excited about, because in this theory, we can solve the cosmological problems, and moreover, we can also we can also derive the scalar tilt and the tensor tilt. And what you end up with is this relation, which is unique. So you have exactly, already you know what is NT based on this theory, and the result is unique. I can't give you more details because I didn't publish yet the paper, it's not yet on the archive. And but this is the strong outcome of the theory. So for example, if the theory is conformal invariant, you have NS equal 1 and T equal 0. If there's no more conformal invariant, you get this kind of relation. And this is unique. This relation between NT and NS is unique. I think, well, if I don't have any more time, I can stop here.
Unfortunately, no.
Okay.
Okay, thank you very much, Leonardo. Okay, let's have just one quick question from Richard, and then we move to the discussion session.
I can't see people. I don't know how to.
Hey, I got a little bit lost in the talk. The operators that were in your, or the operators that were that you built your local operator out of, were they in the presence of a general? Were they generally coordinate variant operators, or were they in the presence of a particular background?
No, any background. That's general covariant theory. General covariant theory.
I'm a little bit confused by that. It seems to me that that's going to lead to new divergences. So if you have the dynamical variable up in the exponential, it seems to me that you're going to get a class of diagrams coming from the operators in.
No, because if you look at this particular, it depends on the form factor you choose. That's the reason because I like to take this approach, which is general covariant.
I don't think it depends on the form factor, and I've done that calculation. I'm not the only one.
Sorry, can you repeat? Sorry,
I don't think it depends on the form factor that you use.
It depends, sure.
I've done that calculation, and I'm not the only one.
If you are worrying about divergences in loop diagrams, you can see from this form factor, I hope you're reading the same slide, that the asymptotic, only this contribution, which is polynomial, gives contribution to the divergences. And then
what about the fields that appear in that box?
Well, box there is the metric, and you can take the variation and prove there is an elegant proof. There are few elegant proofs starting from the paper that you can resum all of this in Minkowski space-time, right? In Minkowski space-time.
So it is the Minkowski operator, not the.
Well, I don't know any other way to quantize the theory beside and to speak about unitarity and divergence beside Minkowski space-time.
What do you do about gauge invariance? It seems to me that.
No, gauge invariance is, I mean, you expand the box in the beginning is depends on the metric. Then you expand in the graviton fields, you get all your vertices, like in Einstein's theory or in any eigenderivative theory.
But if that box is constructed out of the flat space background, you're obviously going to lose gauge invariance. You won't have.
No. Because you have your quantization approach, you have your Popov, you have the same structure like in any gauge theory. Doesn't matter if local is non-local. The important thing is that any operator in this analytic function.
It matters that the operator is being built out of the metric defined in a particular background, right? Sure, that's obvious, isn't it?
When you expand, well, you always expand around the background and you have gauge invariance. Okay. So asking the questions.
I don't want to just keep belaboring this, so I'll drop out and you can go ahead.
Okay, maybe we can keep going on this point also in a few minutes in the discussion sessions. Terry, if your comment or question is quick, otherwise we postpone to the discussion session.
Yes, I think there are many problems with these theories, even though I was involved with them. One is tree level. They have a physical tree level behavior, which is directly connected to their superior normalizability. In other words, if you do 2x2 scattering tree level, you have one factor from the non-local factor from the propagator and two from the vertices, and that gives you a physical high energy behavior.
Well, I don't know what are you talking about, because the amplitude has been computed for this theory for any form factor.
What do you mean?
I show the slides.
You can compute it very easily. It's an elementary computation.
Yeah,
There's
and
nothing
it's the
fancy
same
about it.
Einstein-Hilbert theory. So what's the problem?
The problem is that the amplitude goes exponentially, blows
No,
up exponentially at large
No,
energies.
no, absolutely no. The amplitude goes like Einstein-Hilbert theory. No
No,
exponential. It depends on the theory you are looking at.
it is
This
not a
theory-
matter of controversy. It's simply writing down the graph and looking at it.
No, you don't. You can write the graph. You have to sit down and compute it. And if you do that, that's the result you find.
That's what
Look
I
at
mean.
this amplitude. Look at this
That's what
amplitude.
I
Here
mean. Of
appears
course you
gamma
compute
2.
it.
Here appears gamma 0. And you see all the cancellation. In the end, when you sum all these contributions, you get the Einstein-Hilbert amplitude. Shut up and compute and calculate, right? Like our friend said.
That's not the case. You do, if you do these graphs, they go like exponential k squared. It cannot be otherwise. You don't have a cancellation of the
It's
fold
here the
factors.
cancellation. Look, I'm not cheating. It's here the
All
cancellation.
right.
It's here the cancellation. I'm showing computation, not blah blah.
I think we can make further comment on this because I also have a comment on this. Maybe we can postpone to the discussion session, also field question. And I mean, I think we can just meet again in, let's say in 7 minutes. Okay, so at 7:35. Okay, so let's thank again all the speakers of the second session. And yeah, let's just tell you. So in this discussion session, it's our pleasure to have also Tirtha Verbisbas, who also is an expert in local field theories, periodic string field theory. Tirtha, are you around?
Yeah, good
okay.
to be part of this.
Okay, yeah, very nice. So yeah, you will be the one leading the discussion. So we can start in 7 minutes. Zravan, are you there? You want to say something?
Just I want to point out 2-3 broader questions which are not only just related to this session we just had, also previous